Hi everyone, this is part 2 of the study of generator coil acceleration under load, and this is the test device that I used in the previous video. So if you haven't seen the previous video, look for the same title, and test 1 would be the first one. And in that test I used a solid steel rod like this as my core material, which was located about here, and I would slide that coil on the rod at different position and show different effects. So we're not going to be using that one in this particular video. And by the way, this video is not to discourage anyone or to make them feel that they're not doing the right thing. This is more an informational video, and it's going to be based on my own experience as a free energy researcher and trying to help others understand what is going on in their different setups. So basically what this video is going to be addressing is the core material itself. So what I am suggesting and encouraging is not to use such a core as I just showed. I did that just in the previous video to show that you can get some amazing effects, and it does this acceleration under load, also known as AUL. And that effect is really, interesting to observe, but I don't think it's going to lead you where you want to be. And this is why I'm doing this video, so we can actually all be on the same page together. You've possibly been given this link by someone who is actually trying to help you maybe understand what the differences is when you're testing generator coils with different core material. So if you're using steel rods like I just showed you there, or a bolt, or welding rods, or even transformer laminations, have what's called hysteresis. And hysteresis is basically, here we have a 1/4 inch steel rod, and if I put a magnet on this 1/4 inch steel rod and then take the magnet away, I would be able to pick up some paper clips with it. So this steel rod would become temporarily a magnet for a certain amount of time. That's what hysteresis is, meaning that once a magnet is applied to it, it keeps a residual history, if you want. That's why the term hysteresis, I believe, is used, of that magnet. So when you have that core material that can keep a residual magnetism, it's going to affect your tests, and it's going to give you this effect called acceleration under load. And it's not an effect that's actually going to give you anything extra, and I will demonstrate that to you why. This rod here is the second rod that we're going to be using to demonstrate the differences in efficiency when you do use the correct core material. Now mind you, this is the highest at this time quality of core material, and it's called met glass. And what it is it's very tiny film laminations of a glass kind of steel. It's been anodized to a point where it basically is a very brittle product, and is basically like a glass characteristic. And I will show you that how thin, that's what's in here, all these thin laminations. This is a met glass lamination. It is ultra thin, okay, and it is very brittle. Okay, there, I'll show you some little flakes here that basically can just flake right off, and if you squeeze them together, actually you can even get cut by it because it's very much like glass, but it'll, see there, I just folded it and it just breaks. So it's a very interesting product, and it's I would say one of the highest of quality of core material. So we're going to go and actually go from one extreme to the other. But if you have products that are anywhere in between these two, like I've just described, and you're getting this acceleration under load, I believe that you're really not going to be achieving some extra power out of your device, and I will show you why. So here, this is the coil that we're going to use, which is a solenoid coil, and I will give you the details on that coil right now. I have them all written down. This is by Prime Mover, which is a Dremel tool with a permanent magnet here that is diametrically magnetized, meaning half of it is a north pole and the other half is a south pole, and it's going to be rotating and creating the AC basically sine wave in the core material, and the coil will be put under load. And we're going to use only resistive loads because that's the only way to truly measure power. Using light bulbs or anything else, LEDs, is again something that will give you a false illusion of power. So you really need to calculate power correctly, and I will show you that this is how it's going to be done. That there is a 10 ohm resistor, 1% precision resistor. And we're going to also use a 1 ohm resistor, again another precision resistor, and that's what we're going to use to actually short the coil and to get that effect of acceleration under load. And we're going to observe how much power we get out of the load resistor basically with that condition. And here is the details on the coil. So I've calculated that coil to be about 945 turns of 24 gauge wire, which comes to 51 millimeter, and that's without the enamel insulation. The resistance of that coil, DC resistance, is 5.35 ohms. The inductance of it in air core, as it's sitting there, is 7.66 millihenries. It is 19.22 millihenries when it's on the 1/4 inch steel rod, on the center of the rod, which is the maximum inductance. And on the met glass 1/4 inch rod, it's basically 101.3 millihenries. And both rods are identical in size. The only thing is this one here looks maybe different because I've got this black electrical tape on it so that I don't cut my fingers when I move the coil or whatever, because it's very sharp as well, the met glass. So we're going to be doing tests with the steel rod, and the first test we're going to do is determine a baseline test, and this is my suggestion as well. If you're doing generator coil tests, you've got to start somewhere, and you've got to find out at a certain voltage, and what we're going to be using is 28 volts input, and this will be the current, and then we'll multiply that to get the watts, and basically that's what you need to know: watts in, watts out, and you'll be able to do some more efficient results of your generator efficiency, basically. So the baseline test is basically just turning the switch on and noting how much it takes just to the motor to turn without the core being there or anything. Okay? Then the next step would be to add the core, and we're going to do that. And then the next step would be to add a load to your coil. So we're going to do it in those 3 steps. So basically I have it written down here. So this is prime mover, that's the PM, that's what it means, or baseline. Then with adding the rod, and then adding the load. And we're going to find out how many amps, how many watts. We're going to be able to calculate our difference between what it is when we introduce the rod, how much power it takes in watts, and then when we apply our load, how many watts our load is going to deliver. Now I've actually set up this that we're going to actually, at that 28 volts, we're going to be delivering 3.17 volts on our 10 ohm resistor there. So basically we're only going to be delivering 1 watt, and we're going to see how our efficiencies work here and our differences. And obviously the next test would be to add the met glass rod, and we're going to be using exactly the same. So we're going to be comparing, the differences between efficiency. In this device, in this one here, we're going to get some acceleration under load. This one here, we're not. And we're going to see those results and see if the acceleration under load is giving you a bonus. All right. So the next thing, I'm just going to pause the camera because I got to set this up. Is going to put the rod in. Well, first of all, we can just turn this on now. Let it warm up a little bit. And if you look, there is a 28 volts. And we are consuming 340 milliamps. So 340 milliamps is our baseline at 28 volts. That's our scope, and there is our frequency. If you want to calculate the RPM, we're basically at 138 hertz there, and you would just divide that by 60, and that would give you your RPM, because that's frequencies per second, and you just need to convert that to RPM, which is revolutions per minute, and that would tell you the RPM of that device. We're not going to do any RPM tests. It's going to be very obvious that it's either going to accelerate or decelerate. You can hear it with the motor, and you can see it with the RPM. So that sine wave that you see there is the sense coil here. It's put very close to the coil itself. So we know what the phase of that particular coil is compared to our coil that we'll be putting under load and moving up and down on the rod. Okay, so anyways, the Dremel tool here has warmed up, and we're going to just do one last reading because as it warms up it changes a little bit. So this is our correct baseline, 28 volts at 335 milliamps. So now I'm going to set up a rod. Okay, so now I have the rod in place, and it's being held by this vise, and I've got a little bit of black tape there to keep that from vibrating. It just gets noisy. And the coil is open, it's not closed, it's ready to be tested. And the next test we're going to do is establish how much it costs the prime mover to bring this steel rod here. So this cardboard is here as my gap, so I keep an exact gap as a feeler, so I can slide that in just nicely between the core and the magnet itself. And you see the little bit of air gap that I've got there, obviously, so this magnet doesn't rub on the rod. So we're going to keep that exact same gap for our met glass rod, which will be the next test. So now we're going to turn that on, and we're going to note down from the difference between our baseline and we're going to be, which is now I've calculated, is 9.38 watts. And that's exactly what it's going to also take, obviously, for the met glass core as our baseline. That's where we start. And then just calculate how much it's costing us to have that rod there. So now we go ahead and start this up. And I guess some of you can hear that it's not turning as fast. And if we look at our frequency is much less. And our current has gone up. So we're at 434. Probably once it warms up a little, it'll probably be around 433 milliamps. So we're going to write that down. 433 milliamps is our baseline, is once we have the rod introduced. Okay, so now the next thing is we put our coil on load. Okay, let's take note. Okay, well, I guess it's warmed up a little. We're probably closer to 430 milliamps. As it warms up, it changes a little. So we can note that. And we can see our RPM. So we're at about 97 hertz. And now we're going to put our 10 ohm load on load. And we can hear an increase in RPM. But we're not, this is our voltage across our 10 ohm load. We're still in the milliamps. So it is small. It is not very delivering much power across it. And but we did have a boost in RPM. Note as well that there is a phase shift between the oh, I have my probes upside down here, so I'm going to have to bear with me for a second. Okay, there, that's better. This is our sense coil, and this here is our coil under load. And I will expand on the voltage division here, so we have a better look at the phase shift. And just look at this size here, and that's the amount of difference we have in the current from the sense coil at the front and the current across our load. And that is part of the effect. And now I'll bring the coil in, and you'll notice and you can hear an increase in RPM. Okay? And this is about the maximum RPM right here under load. And if we see now, our load has, I'll show you the phase shift. So this is going back, this is going forward, and that's about maximum acceleration there. Okay, and if you look at our RPM, I'll go back, or our frequency, which is reflecting the RPM, and now I'm going forward. And there I am about at the halfway point, and that's about its maximum RPM. And if I keep going forward, you're going to see that it's going to now start to go down in RPM. But we are delivering more power across our load. So what we're going to do now is we're going to drop this down, and we're going to take more samples so we get a correct reading here of our volts. RMS value is the only value you really want to have to measure across your resistor, so you can convert that into watts. You really need that as well. And your sine wave has to be clean if you're using a multimeter. If not, you have to use an oscilloscope to measure. Now, what I'm suggesting to do now is, basically we had 433 milliamps, or it went down to 430 milliamps when we introduced the rod without the coil under load. And I'm suggesting that we bring this coil here forward so we get basically that 433 consumption. So we're basically going to be going right back to where we were. So I'm going to need to put a clip here to hold the coil, because the coil, that's an interesting thing. The coil wants to naturally, it pushes itself back, okay, which is the flux battle between the front end of the magnet and the coil itself. So now I'm holding it with this clip here, and basically we're going to bring this to where we had started. And what I'm going to do is I'm going to disconnect the load temporarily and just see where we're at, because it changes as you're warm. So 426 milliamp is where it is at now without the load. So I'm going to connect the load, and there we go. We're again at 426, pretty well. I'm going to drop that a little back a little bit. Okay, so we're at 426 with the load, and I take the load off, and we're at 426 as well. Let's connect our load back on. Okay, so basically a lot of people are saying, well, I'm getting basically, let's see what we're getting here across our load. Okay, we're getting 3.2 volts RMS, okay, which is a little tad over 1 watt. So basically, people would conclude that now we're getting 1 watt for free, because if I disconnect it or I connect this load, it's not changing my power input to my prime mover. Okay, so that is a common conclusion that people are making, and we're going to be observing that to see what happens with the net flash. So that's the test that I wanted to do here with this, and the next test would be to put the 1 ohm load on this as it is. And I have to pause the camera to do that, and I will show you that we'll get acceleration under load even with the coil at this position still, but the power that will be dissipated across that resistor will be next to useless. So let me set that up for you now. Okay, and maybe I'll just give you a phase shift view here before I do that. So here we have the amount of phase shift that we have between the front end and that coil under load. So there is definitely a phase shift, and it's reduced because we've gone close, and just so that we have basically a neutralization. And like I showed you, if I remove the load, we have no change in our input to our prime mover, with it on or off. So there you go. Now I'm going to pause the camera, and we're going to put the 1 ohm load without changing anything here. Okay, so there you go. That is the 1 ohm 1% resistor there, and we're going to connect that. I haven't changed anything. Coil is still at the same spot, and there is our input to the prime mover, and let's connect that. Wow, we're getting acceleration under load. Exciting. Okay, so our current has gone down. Where is our waveform? It's buried. Okay. So here you can see that we have a little more phase shift again, once again. But that is what is across our 1 ohm resistor. 378 millivolts, so 0.37 volts. Far from being anywhere of the power that we had here. We're delivering 1 watt here, and now we're in the milliwatts here. So it's really interesting to see this, but basically when people are demonstrating that, they are not utilizing the power from the coil, and that's what I'm demonstrating in this demonstration. So even though I bring the coil further forward, okay, as I'm doing now, we are capitalizing a little bit more. We've gone up to 450 millivolts, but that's about the max that I can do there. So I just thought I would throw that in so that people could see that power cannot be maintained on a low resistance load or a short circuit. The short circuit demonstrates nothing. Basically, if I short circuited that, I wouldn't be able to measure 1 millivolt across 1 millivolt across this coil. It would just flat to zero, and there is no reflection of power. So don't be fooled by tests like that. They have no value unless you've got some device to measure it to determine if it has value, like I am doing here for you. So that's it for testing the solid steel rod. The next test now will be the met glass core. Okay, the met glass rod is in place. The coil is open, not under load. This is the previous test with our steel rod. So basically we had 9.38 volts, 38 watts, sorry, as our baseline for our prime mover turning. To introduce the rod only without putting it under load, it brought it up to 433 milliamps. I know it went down as it got warm or whatever, and but we're just going to keep that there for now. It's fine. 12.12 watts. So basically it cost us 2.74 watts to introduce that rod without asking, without pulling anything out of our generator coil. But we got that acceleration under load, which just basically we're able to negate our generator coil. So I leave that as well at 433 milliamps. So basically our coil under load, it took again 12.2 watts. But basically we are delivering about 3.17, and in fact it was about 3.2, but basically 1 watt was what was being delivered by our load resistor. So even though this was really exciting here to see that we can actually deliver 1 watt without having any effect back onto our prime mover, you know, this 1 watt we delivered, but yet it cost 2.74 watts for our core to come to the magnet rotor. So I don't see this being a very efficient generator in a sense. Now a lot of people say we don't calculate the core losses, we just start at this point. That is true, but if you're into free energy, I don't see how you're going to get any free energy out of this scenario here. And that's what I'm trying to indicate, excuse me, and help you with. So now we have our met glass core in place, and that's securely clamped there. Hopefully it won't move. I have my air gap paper here to show you, and it is the identical air gap that we're going to use there. And coil is open, we're ready to go. Our voltage is at 28 volts. We're just going to start our motor. And you may notice that the motor is turning faster. And this is vibrating off the table. And you're right about that. And actually I have to bring down the voltage division here. So let's have a look at a few more samples here. So we're actually at 120 hertz. So divide that by 60 and you'll have your RPM. Now that's our coil open, but that's basically the difference. Bringing this core, this quality core, will not dampen the speed of the motor so much. And if we look at our power, it's way down compared to the other solid steel rod. So we're basically at 372 milliamps, and we're going to write that down. So 372 milliamps is the cost of bringing the core to the magnet rotor. And now we're going to put our coil under load. So our coil is under load. You may have noticed a small amount of acceleration. There is. And if we look, we're at 122 hertz. because the coil is the furthest away from the rotor. And I would say that my guess why it does accelerate here is because of the phase shift between current of the two. So if we look here at our front sense coil, we have a good phase shift there. And if you look at our current, it's gone down. So we were at 372 and we're down to 371. I've removed the coil, the load, and you see the current goes up a little and the RPM drops a bit. I'll now connect it. So you see an ever so slight increase in RPM and a small drop in current. Okay, now we're going to slide the coil forward and I'll show you the phase shift, what happens. So as you see, the phase separation between the front sense coil and the coil under load is changing. So that's as you're going this. And obviously you're hearing the RPM drop as well. And the current is going up as well. So what we'll do now is we're going to set this. Going to need my clip so that this coil delivers the same amount when we were using our solid steel rod. So we need to achieve 3. I'm going to have to get more samples here. We need to achieve 3.17 volts RMS. Okay, so close enough. We're exactly there, 3.17, and we can actually go in a bit more. Okay, so we're actually pretty well identical to where we were. Just get a little more samples there, make sure we're comparing the two the same way. I just brought it in a bit more. I'll put it at 3.19 there. That's pretty well identical amount of power we're delivering here compared to the previous test. However, if you note, the current is still lower. So it's taking basically 400 milliamps to deliver 3.18 volts across our load resistor. So we're going to write that down. Here we're taking 400 milliamps to deliver basically 1 watt. To our load resistor. So now we've got to figure out these numbers here, and I will come back with that. The next test we can do as well is attach our 1 ohm resistor, and I'm going to stop the camera and do that. So I think that's it for now. Okay, I've attached the 1 ohm resistor. It's ready to connect, and the coil is still exactly in the same position. This is just to determine if there is acceleration under load as well in using this met glass core. And as you saw, as I approached this coil to the rotor, we didn't get the same effect as what we did here. But rather, we had a lot less power input. And that's what we're going to compare, is the efficiency, and to see if the other way is a valid way of calculating efficiency, or claiming that we're getting power out without affecting the prime mover. So now I'm going to start this. It's a little noisy, I know, and what we're going to be looking at is basically the RPM of this, and we're going to connect the load and see if it accelerates. And it did quite a bit with the other core, and but we're not delivering much power, and we'll see if this is any better. So the coil always moves forward, so I'll have to reposition it back, and we'll connect that. First we got to look at our frequency. So there we are, just basically under 120 hertz. There we are at 120 hertz with it warmed up. And now I'll connect the coil. Position that correctly here. And yes, we are getting a little increase in acceleration, okay? And that may be due to the phase shift. But let's look at our the amount of power we're putting across. So the Met glass core is better, a little better than the other core, and it's delivering 325 millivolts across our 1 ohm load. Still a very small amount of power, not very useful. So obviously a dead short would accelerate it even more. I'll do that for you. And there you see it right away, 124.5, 0.6 hertz. So, but again, when it's a dead short, there is no power, so that is useless test. So the next thing is now to calculate our differences here and see the value of this experiment. Okay, so here are all the results. So basically this is our steel rod here test, and the prime mover without the steel rod present was basically 9.38 watts. We introduce it and we use the power consumption of the prime mover goes up to 12.12 watts. So basically our total increase, okay, without putting the coil under load is 2.74 watts if you deduct this from that. So that is how much power has gone into the system to prepare it to become a generator. Once we put the generator under load, we get this amazing acceleration under load, and I was able to bring it back so that we actually take no power from the prime mover. No apparent power anyways for the time. So basically it cost us 0 watts to deliver 1 watt, okay? So we take our 1 watt and we deduct off of our total that the difference is from the prime mover turning on its own without the generator coil present, which includes the core obviously. It cost us 1.74 watts to deliver that free 1 watt. All right, so that is how I'm looking at it. But like I say, many people don't factor in these inefficiencies of a generator. But if you're working towards free energy, you have to consider this. So now let's look at the Met glass rod. So basically we start with the same as our baseline here, okay? But our Met glass was a lot more efficient. When we introduced the Met glass core, it basically went up to 10.41 watts, which was actually a 1.03 watt increase. So pretty well 1 watt increase by introducing that rod. Kind of interesting and coincidental. Then we put it on load. We don't get serious acceleration under load, and definitely not when we're trying to output some power on our load. Okay, so it actually went up to 400 milliamps, and basically then we are at 11.2 watts. Still pretty darn efficient. It's not even gone up 1 watt. Basically that means that when we have our rod introduced and then we put our coil under load, it actually only took 0.79 watts from our prime mover to deliver 1 watt. And quite different from our scenario up here. However, it did take power, so we're going to actually add these two, the introduction of the core, 1 watt, and our 0.79 watts to actually make it 1.82 watts to deliver our 1 watt. And basically we're under unity by 8.82 watts. Here we're under unity by 1.74 watts. So there is the difference, and those differences are mostly caused by the core being bad quality. So we're comparing here one extreme to another. This is the worst case scenario, but then I say as well that welding rods are definitely not a suitable core material, mostly if you're working with higher frequency. As you increase the frequency, you're increasing eddy currents. And there's huge amounts of eddy currents in this core itself. Eddy currents basically can be alleviated by thin core laminations. And this is a solid core. And those thin core laminations have to be insulated from each other, meaning no short circuit between each one of them. So this has nothing of that. So that's why we have such a huge waste here. But the better of the scenarios would be transformer laminations, but as well with my tests I found transformer laminations to also have a certain amount of hysteresis for sure when you go over the frequencies that they've been actually intended for. They're intended for about 60 hertz, and the hysteresis under 60 hertz frequency is not very great. And but when you increase your frequency, we were operating in the 120 hertz range, which is double the frequency. Now you're actually having your hysteresis, meaning every time the magnetic flux changes poles, is getting shorter and shorter time between the two, and that causes losses. And the other big loss in this here is eddy currents, and basically you can feel it by the heat. So if your core heats up, you touch it after it's been running, you have losses there. So this one heats up definitely. The met glass, you cannot feel a single bit of temperature difference. So that is what's going on, why this is so much more efficient. And when you have the hysteresis taking place in the core and the dynamic between the load of the coil and the core, I believe that's what's causing your acceleration under load. So there is a little bit of that using the met glass, because there's probably a small amount of hysteresis still left. It's not perfect. There is no such thing as an ideal core material yet, anyways, that I know of, but it's a lot better and getting closer to being more efficient. In the next video, I will show what we can do with phase shift and how we can actually change a little bit of what I've done here to make it even more efficient. And obviously we'll be only using the met glass core. This video is just to demonstrate the huge differences and the potential lack of understanding of what's going on in this acceleration under load, and thinking that you have the holy grail there. So hope this helps, and like I said, I'm not doing this to discredit anybody's work. I'm just doing this to bring awareness and to help my fellow researchers out there. So I hope this has been a helpful video, and thanks for watching. Bye now.